In this video, we'll discuss some preliminary theory about higher order differential equation. Basically, we will first give two definitions. One is initial value problem, and also give some result, right? Some result about initial value problem. Under some conditions, we will give a sufficient condition such that such a problem will have a unique solution on some interval, right? Interval will also be determined. And also we will mention what is boundary value problem. They are different. So under some conditions, initial value problem will have unique solution, but what's that? Boundary value problem could have no solution or many solutions, infinite many, or sometimes one solution. So that really depends on what's the boundary conditions. Okay, let's start from the initial value problem, revisit, right? So initial value problem. Initial value problem. Uh, value problem. So basically, we'll discuss the linear nth order differential equation. So it's about linear nth order differential equation with nth order range. I'll just draw an order. So basically, linear means linear in the term of the y prime all the way to nth derivative. Nth order means the highest degree of highest order of derivative is n, right? You can take like a second order means second derivative at most, and linear means we can never have a term contains y times y prime. The degree of each term in term of y prime all the way to nth derivative must be 1. So linear or 0, 1 or 0, right? Degree. So basically what we want to solve here is we want to solve a linear nth order differential equation, which is given by general form is ANX, right? That's a function of x, coefficient function, right? So times derivative of y, nth derivative of y about x, and plus an minus 1 x times dn minus 1y over dx n minus 1 all the way to a1 x times dy over dx plus a0x y equal to g of x. We want to solve such a linear nth order differential equation. That's a general form. We have a standard form. If you move all the term doesn't contains nth derivative to the right side, then make a division, right? We have a bunch of initial conditions. So subject to some restrictions here is y of x0 equal to y0 all the way to y of y n minus 1 derivative, right? Which is dn minus 1 y over dx n minus 1. And plug in x0, you get y n minus 1. So x0 is a number, and y0 all the way to yn minus 1 must be initial condition, must be some number, right? This is our initial condition. Okay, so we will give a existence and uniqueness result first, right? Existence. Under some condition, we will not prove it in our class. Using some math result, we can prove such a result. Such a equation will have a solution under some sufficient conditions. We suppose all the coefficient functions a n x all the way to a0 x, and also the right side function g of x are continuous on the interval I, might be 0 to 1 or 0 to infinity or just some interval, right? And one more condition is ANX is never equal to 0 for any x inside I. If you choose an arbitrary point inside I, then this ANX, the leading coefficient, is never equal to 0, right? Otherwise, this is not true. The result is not true. So if good thing happens, x0 happens, is inside our interval, then what? Then a solution y of x of the initial value problem. So this is our initial value problem here, right? IVP star exists on I and is unique. You can only find one solution, and this solution must exist. So let's recatch the conditions. All the coefficient function together with g of x must be continuous. And also, the first coefficient a in x can never be 0. So let's see some example, right? Let's try to see how this result help us to understand the differential, understand the initial value problem range. So let's see some examples. And the first one here is we are given an initial value problem, which is the third order, 3y sub triple prime minus 5y double prime minus y prime plus 7y equal to 0. So that look like a very complicated differential equation. But if you have such an equation, one thing you should notice is you have a trivial solution, which is y equal to 0, right? When you have y equal to 0, then y prime has to be a 0, y double prime, y triple prime, all are 0. So this will be satisfied. We are also given an initial condition, which is y of 1 must be 0, y prime of 1 also equal to 0, and y triple prime of 1 also equal to 0. So now you can see that by our existence uniqueness, all the coefficient functions are continuous everywhere, right? In this case, the interval of existence is from negative infinity to positive infinity because 3, 5, negative 5, negative 1, 7, 0 are all continuous as constant functions. It's continuous everywhere. And also 1 must be in there, right? And also we know that y equal to 0 is a trivial solution, right? So y equal to 0 is the unique solution of the initial value problem, right? This initial value problem here has a unique solution, which is y equal to 0, right? And now let's see another example. Second example, our what's that called? The differential equation is given by y double prime minus 4y equal to 12x. right? And the initial condition is given by y of 0 equal to 4 and y prime of 0 equal to 1, right? And um, so you can see that uh, um, well, I think we will try to solve this later, give a procedure to solve this. But you can verify that uh, y equal to 3e to 2x plus e to negative 2x minus 3x. So this is a solution of our initial value problem. And because this all the coefficient and also the function on the right side are continuous everywhere, right? So this thing, after you verify this is a solution, this is a unique, all continuous, unique solution on the interval I from negative infinity to positive infinity, right? So this function, by our existence and Unix result, uh, after we verify this is a condition, is a solution of this, and then we can conclude this is the unique solution of the initial value problem over the interval from negative infinity to positive infinity. And later we will develop a procedure to identify such a function, right? We will have a way to determine the solution. Now, from our existence and what and uniqueness result. We know this is a unique result. Third example, we have here is we are given a initial value problem, which is x squared y double prime minus 2xy prime plus 2y equal to 6. We know that y of 0 equal to 3 and y prime of 0 equal to 1, right? Now you can see that this one doesn't satisfy the condition given by our theorem, right? Now you can see that the theorem here require all the function must be continuous. And now you can see that x squared and negative 2x and 2, 6 are continuous on the interval from negative infinity to positive infinity. But the second condition is not satisfied. Second condition here is a n x cannot be 0. But you can see that x squared equal to 0 when x equal to 0. So the coefficient of the leading derivative could be 0 in this case. Now this is not true. Condition is not satisfied. And you can verify this equation have a solution, have infinite many solutions, right? So well, you can verify that y equal to cx squared plus x plus 3 is a solution of the initial value problem for any C, right? So this theorem, sufficient condition are also very important. You have to satisfy all of them to get the existence and also uniqueness. So this is basically what we want to know about initial value problem. When do we have a solution, right? As long as all the coefficient function plus the function on the right side are continuous over some interval, which contains the initial the condition at the specified point, right? And I contains 0 in this case, right? And so that's then, and also the leading coefficient never equal to 0 on I. Then the solution is unique. If you have a solution and you get a unique solution, right? The solution must exist. Okay, now let's go to our second class of problems, boundary value problem, right? So let's go to our second class of function, which problem is called boundary value problems. If you look at our initial value problem, now you notice this initial conditions are given on a specified point. All the condition is given on x0. In this case, x0 will be always same. So if you have some conditions given on different points, right? At different points, the first one is on x0, second one is on x1. That's called boundary value problem, right? So sometimes in real life, if you want to model some phenomena, so you naturally get boundary value problem instead of initial value problem, right? So this we will have an example of general formula for linear second second order. So second order, basically you want to solve a2x second derivative, not s derivative, second derivative plus a1x times y prime and plus a0x times y equal to g of x, and also subject to some boundary conditions, right? Boundary condition is given by y of a equal to y of 0 and y of b equal to y of 1, with a, b are different. So this is called the boundary conditions. Boundary conditions. In many applications, it's more natural actually. And so remark here is such a boundary, we don't have a nice result about the solution as the initial value problem. The remark here is a boundary value problem can have many or one or no solutions, right? Many solutions or one solution or unique. Everything is possible for a boundary value problem. So let's discuss example here. In this example, this boundary value problem has many solutions, right? Example here is we know that x equal to, I think we checked this before, c1 cosine of 4t plus c2 sine of 4t is a solution of x double prime plus 16x equal to 0. If you want, you can check that again, right? You take the derivative twice and plug into our equation. The equation will be satisfied. So let's give a boundary condition here. So boundary condition means the condition is not limited to one point, right? We have x 0 equal to 0 and x pi over 2 also equal to 0, right? So let's try to see how what are the solutions of this boundary value problem. Differential equation is that, and boundary condition is that, right? So what we can do, plug the boundary condition into our solution, right? You get two equations. So 0 equal to C1 cosine of 0 plus C2 sine of 0, 4 times 0 is 0, right? And 0 also equal to C1 cosine of 2 pi, 4 pi, I mean, pi over 2 times 4 is 2 pi, plus C2 sine of 2 pi, right? If you try to plug in number, cosine of 0 is 1, sine of 0 is 0, cosine 2 pi is also 1, sine of 0, sine of 2 pi is also 0. So both equation implies C1 here is 0, but C2 here is arbitrary. So you can choose whatever number you want. This system will be satisfied or arbitrary range. So x equal to C2 times sine of 4t is a solution of the boundary value problem for any C2, right? You have infinite many solutions. Okay, so that is about it, right? So in this video, we discussed two kind of problems, right? One is initial value problem, the other one is boundary value problem. And the only difference is initial value problem, initial conditions are given at a specified point, only one point. But boundary value problem, your condition is given by given at a different point, at least 2 points, right? Could be different derivative, but at least 2 points. So for initial value problem, we have a very, very nice result about existence and the uniqueness of the solution, as long as the coefficient function and the function on the right side are continuous over some interval. The interval contains the initial condition point, and also a and x can never be 0 inside at I, the interval, then the solution exists, and also the solution is unique. We have three examples. First two says condition satisfied, you have a unique solution. And the third one says the conditions are not satisfied, you have infinite many solutions. And boundary value problem is basically solving a differential equation subject to some boundary conditions. Boundary conditions just means you have conditions given at different points, right? Remark here is for any boundary value problem, this boundary value problem could have many solution or one or no solutions. We don't have a good condition to specify this one has exact one solution, right? Because now you can see that that's a function like this. All the coefficients are continuous everywhere, and also the leading coefficient is not 0, never be 0, right? So still you could have like many solutions. So for boundary value problem, we don't have a nice result to classify when the boundary value problem has a unique solution. Okay, I hope you will. Okay, I hope you get something right from this video, and okay, we'll stop here.